All right, so for chapter 11, we're in section 6, and what we want to do is this is going to be a quick video. We're not actually going to do any examples in this video. It's just going to be more for informational purposes. But I want you to just take a look, be exposed to some different types of surfaces, right? Because that's the point of this section. Let's start with some of the surfaces that you've seen so far. In previous videos, you've seen, for example, the equation of a sphere, and we've just got done studying planes. So these are some surfaces that you are aware of so far. Let's just add to those, and we'll start with the idea of a cylinder, right? Or what we're really looking at is cylindrical surfaces, right? So the surface of a cylinder. So follow me to this picture right here. So starting with just a basic right circular cylinder, and what we have here is we have some circle and say in an XY plane, say, and if you were to move that circle normal to the XY plane, right? So if you were to move it up and down the Z-axis, you could build a cylinder from that, right? You could build a Coke can from that. The key idea of this type of surface, I will read this definition to you, but I'll try to give you in other words so that you can follow me. So let's start with just, before we talk about cylindrical surfaces, let's just start with the definition of a cylinder. So it says, let C be a curve in a plane. And you can see my arrow. So for example, this circle would be a curve in a plane. It doesn't have to be a circle, right? Just C is, in other words, C is a curve. All right, and let L be a line not in a parallel plane. So notice how this line L touches that curve C at one point, and you can see how it's running perpendicular, meaning it's not in a parallel plane. Okay? So far so good. I'll give L and C a name in just a second, but the set of all the lines parallel to L that intersect C is a cylinder. So if I were to draw another line L, right, so that's parallel to L, and that touches C, and if I drew another one that's parallel to L that touches C, all of those lines form the cylinder. Let me just give a few of these a name. So we refer to the C as I refer to it as a generating curve. You also might see textbooks refer to it as a directrix. But it's the curve. C is what forms the type of cylindrical surface that you're dealing with, right? This looks like a Coke can, in other words, because C is a circle. If C was more elliptical, then the cylinder would not look like a Coke can, right? So C is the generating curve for the cylinder. And to kind of continue here, so we refer to L as the lines parallel to L, that we call these the rollings. All right. And the last thing really kind of to take away is to take a look at your cylinder. So I want you to understand that, notice that there are only two variables in cylindrical surfaces. And there, in this particular one, there's an x variable and a y variable. The a is not a variable. It's just like the radius would be fixed of a circle. You would know, in other words, the radius from here to here would be known ahead of time. A would be known ahead of time. So if you see an equation, right, with just two variables, and this, I'm speaking a little bit too informally, to be honest, but the fact that there's only two of the three variables, x and y, not z, is a good indicator that you're dealing with cylindrical surfaces. If you see x squared, y squared, and z squared all in an equation, you can be sure that it's not a cylinder. All right, next type of surface, just to be aware of, is what we call quadratic surfaces. These types of surfaces that you're looking at here, these are the three-dimensional analogs of the conic sections, right? So conic sections like the parabola, the ellipse, the hyperbola, right? These are just three-dimensional analogs of that. And you can see the equations, right? Notice, just first off, just to compare and contrast, notice that now we have the z, the x, and the y variable in the equation. That tells me at least that it's not going to be a cylinder. But I don't want to, again, I don't want to spend a lot of time here. The reason why I'm not spending a lot of time here is I'm not going to have you plot by hand surfaces like this, right? There are ways of doing it. I had to do it when I was in college without access to software, but I'm not going to put you through that. So all I'm doing right now is just an informational chapter of just so that you're aware. So anyway, so there's a few different there's 6 basic types of quadratic surfaces, and I have them produced on each page here. So here's the 6 basic types. And finally, the last surface that we're going to study is what we call a surface of revolution. Now, let me see if I can. I'll start by reading it. So, if the graph of a radius function r, I'll talk about that in just a second, is revolved about one of the coordinate axes, right? Then the equation of the resulting surface of a revolution has one of the forms listed below. So that radius function, r radius function. So take a look at just using the picture that I've provided here. And this particular picture, let's think about first off the surface, right? So this is the entire surface of this. Why do we refer to r of x, r of y, r of z as a radius function? And I think you can kind of see it from here, right? So you have a circle here of radius r, and that the radius will change based on what? Based on where you are on the z-axis. Don't you agree with me that if this point was down here, that your radius would be much larger than where it started, right? So that the idea that r of z is what we mean when we say a radius function. In this particular case, the radius is a function of it's a function of where you are on the z-axis. Different places on the z-axis are going to have a different radius. So in this particular picture, y is equal to r of z, right? So take this particular point right here. This is one point on this surface. This point is located at x is 0, y is r of z, and z. So another type of surface. Finally, it's just the idea of if you have a generating curve like this. So say you had this curve, and you were to rotate this about the z-axis. Now you can imagine that curve just rotating around the z-axis. You would form the surface that you're looking at. All right, so again, quick and to the point, just wanted to expose you to some different surfaces. I'll see you in the next video.